Hey guys, so welcome back to your next class. And today we're going to be talking about another property of atoms, that is, and how it is changing when we are looking at the periodic table. Okay, so this property is what we call as um, ionization energy. Okay, it's a big word, but it is quite simple. Okay, so just focus on the words ion and energy. Okay. So we know what ions are. Even in the previous class, we spoke about how ions, the size of the ions, and dependent on the atomic radius. So whenever an ion is formed, the amount of energy it takes to form it is basically ionization energy. Okay, so specifically we talk about creating positive ions in ionization energy. Okay, it's also called as ionization enthalpy at times. Okay, enthalpy also means energy. So this is typically done when we take a single gaseous atom. Okay, so we're going to be taking a single, or more specifically, let's call it a neutral gaseous atom. Okay, it means the atom is vaporized in the form of a gas. It's not a solid or liquid. We take a gas. Okay, so if I have to define it, I'll call it as the amount of energy required to remove an electron uh, from a neutral gaseous atom, or to create an ion out of a neutral gaseous atom. Okay, and generally we talk about removing electrons from the outermost shell. So I can say ki the amount of energy required to remove an electron from the outermost shell of a neutral gaseous atom is called as ionization energy. Okay, I'm going to repeat that. The amount of energy required to remove an electron from the outermost shell of a neutral gaseous atom. That energy is called ionization energy. Okay. Now, why do we say ki energy is needed? Okay, we already know that no matter what atom we are looking at, there are positive parts to it and negative parts to it, right? There are positives inside the nucleus and the negatives outside the nucleus, right? Are protons and electrons. We know there is a force of attraction between the protons and the electrons, right? So if we have to take out an electron from the outside, we'll need to use some energy, right? For example, think about magnets. When you have like two magnets stuck together, you can't separate them without effort, right? You need to give some energy to pull them apart. And depending on the strength of the magnet, the strength you put is also going to be different, right? If it's a small magnet, it's easier. If it's a very strong electromagnet, very hard to pull them apart. You need a lot of energy. Think about it on those lines. So the energy that we need to use to remove this electron from the atom, from the outermost shell, will be called the ionization energy. Okay, now if I have to write it as an equation, I'll write it something like this. I'll take an atom M. I'll just take it as M for now, just some random atom. We give some energy to it. Okay, when we use that energy, that is when that M becomes a positive ion. Since we are removing electrons, it becomes positive. Okay, plus this electron that comes out of it. Okay, so the neutral atom provided energy creates a positive ion or cation along with the electron which is removed from it. Okay, so generally when this happens from neutral to positive, we call this as first ionization energy. Okay, if we take an already positive atom, already positive ion, then give more energy to it. Now we're taking out one more electron, so that becomes 2 plus. Okay, this is called as second ionization energy. Okay, second ionization energy. So the number of times you keep removing, you keep adding them. So I'll call this as IE1, I'll call this as IE2. Okay, now generally the second ionization energy is more than the first ionization energy. You need more energy to remove it from the ion than from the neutral atom. It's quite simple. You can follow the reasoning that we had yesterday. If you can think of it, put it in the comment, that will be excellent. Okay, now since it's energy, we have a unit for it, that is kilojoules per mole. Okay, so kilojoules per mole is a unit that we use for this ionization energy. Okay, how many kilojoules to create ions out of 1 mole of atoms? Think of it like that. Now, how does this ionization energy vary in the periodic table? When we look down group across a period, how does it change? Okay, so if I look down at a group, okay, I'll just go to the periodic table again. While I go down, we know one thing, that generally this atomic size is increasing, right? So as the atom is like a little bigger, it's much easier to remove electrons from the outside. You don't need so much energy, right? Think of it as separating magnets that are very close to each other and separating magnets that are like not that close to each other, right? The attraction between them will be less, right? So it's easier to remove from here than to remove when they're like very close to each other. Think of it like that. So I can say that when I go down the group, the ionization energy for the atoms decreases. Okay, as I go down, the bigger atoms don't need as much ionization energy as the small atoms do. Okay, now what about across a period, when I'm going from left to right? Okay, when I'm going from left to right, we know one thing, that the atomic size generally decreases, right? It becomes smaller and smaller. It means the electrons are much held tighter and closer to the nucleus. So because of that, removing them needs more energy as you go towards the right. Chlorine atom, for example, is smaller than sodium atom. So chlorine atom needs like a little more effort to remove it. So I can say that when I go from left to right, the ionization energy will increase. Okay, the last elements have the highest ionization energy, the first ones have the least ionization energy, meaning how much energy you need to remove. Keep that in mind. Okay, now so these are the general trends, but ionization energy depends on more than just one factor. It's not simply a matter of size. Okay, there are multiple factors that will affect the ionization energy of these compounds. What are these factors? Is that one is nuclear charge. Okay, nuclear charge, we know what nuclear charge means, right? So the amount of positives and the negatives that are combined inside an atom. When the nuclear charge is high, it's more difficult to remove the electron. You need more energy. So any atom with more nuclear charge will have need more energy. Simple example, chlorine, sodium, like we just said. Okay, it's not just the size of the chlorine, but the size comes because of the nuclear charge, right? So nuclear charge will affect. More nuclear charge means need more ionization energy. Another thing is called something called screening effect. Okay, Now, what is the screening effect? So what happens is, as the size of your atoms like kind of grows bigger and bigger, the distance between the nucleus and the outer shell is reduced, right? So these shells that are in between the nucleus and the last shell, they kind of create a protective layer. It kind of protects the last atoms, last electrons from the attractive force of the nucleus. Okay, it's simply not just the distance, it's also the other electrons in between that form a shield between these two. So it's also called as a shielding effect. Okay, so with bigger atoms, because of screening effect, it's easier to remove. You don't need so much energy because the attraction is not high. Okay, so bigger the atom or more the screening effect, less the ionization energy that is needed. Now, one more thing is something called penetration power. Now, what is this penetration power? Okay. Now we know that every shell has orbitals within them. We have s, p, d, and f, right? Now, each orbital has different energies, and accordingly, they also are much closer or farther from the nucleus. Okay. S is much closer to the nucleus than p. P is closer than D, D is closer than F. So I'll say that S is closer, then P, then comes D, and then comes F. It's much difficult to remove electrons from S orbital than it is from F orbital or D orbital. Okay, so if the electrons are in S, it is you need more energy to remove them, and if they're in F, you don't need so much energy to remove them. Okay, so the penetration power of which electron uh, and which subshell they are in will depend on how much energy you're going to need. Now, one more thing that we have is configuration. Okay, what is this configuration now? Okay, some atoms have something called a stable configuration. Okay, for example, if I look at oxygen, I know oxygen has 8 electrons, right? If you remember, we write it like this: 1s2, 2s2, 2p, 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is 1s2, 2s2, 2p, 4. But if I look at nitrogen, nitrogen is 7. So I'll make it like this: 1s2, 2s2, 2p, 3. Okay, this is nitrogen. It's much easier to remove electron from oxygen than from nitrogen, because although since we're going from left to right, nitrogen comes first and oxygen comes later, oxygen should be more difficult to remove, right? Because oxygen is smaller than nitrogen. But actually what happens is nitrogen has something called a half filled configuration. If you see the p orbital here, it's exactly half filled. When it's half filled, it is somewhat stable, we say. So because of this stable configuration, you need more energy to remove the electron. Okay. And finally, coming to atomic radius. This is something that we have already discussed just when we started the topic. Okay. It's quite simple. Smaller the radius, more the strength, and more the attractive power, and more energy we need to put to remove it. So smaller radius, high ionization energy; big radius, less ionization energy. Okay. Now remember just that one key point: ionization energy is how much energy we are putting in the effort to remove the electron. Okay. So that's it for now. This is all I want to talk about today: ionization energy. Tomorrow we'll come back and talk about more different values and how they are changing when we talk about the periodic table. If you have any doubts, comments, please drop them below, and I'll see you again in the next class. Thank you so much.